Welcome to this explainer. Today, we're diving straight into something really fascinating. Why gravitational wave science is rapidly maturing. We're talking about a massive shift from a field defined by rare, highly celebrated anomalies into an incredibly robust, data-driven window into the universe. You know, for a long time, measuring the literal ripples in the fabric of space-time was an exercise in extreme patience. It was a field defined by data scarcity. But, as we're going to see, that status quo is completely shattering.
Think back to 2015. Remember the loud global fanfare of that very first detection? Catching just a single binary black hole merger was enough to trigger worldwide press conferences. People were literally popping champagne corks across continents. Fast forward to 2026, and the contrast is absolutely wild. The fifth gravitational wave transient catalog, or GWTC5, just dropped with virtually zero mainstream fanfare. It just casually added 172 new cosmic collisions to our records. But here's the thing, this quietness, it isn't a sign of failure. It's actually the ultimate sign of success. Black hole mergers are now thoroughly, routinely incorporated into standard astrophysics.
So, let's jump into part one, from novelty to normal, and look a bit closer at this maturing science. We can actually use the history of exoplanet discovery as a perfect blueprint for what's happening to gravitational waves right now. If you remember astronomy in the 1990s, discovering a single planet outside our solar system was this agonizingly slow trickle. Every individual exoplanet was front-page news. But then, the Kepler Space Telescope launched, and suddenly, that trickle became an absolute flood. The field evolved from basically stamp-collecting individual novelties into a fully independent demographic science. Gravitational wave astronomy is crossing that exact same threshold today. What's really crucial here is that having hundreds of detections allows us to move past just admiring single explosions. We get to start modeling the actual demographics of the cosmos. When your sample size hits the hundreds, you aren't just saying, wow, look at that massive black hole. You're actually able to ask, okay, what is the typical lifespan of these systems? Where are they primarily coming from? How do they form? The novelty gives way to deep, foundational scientific value. Moving right along to part two, the stellar graveyard, where we'll look at how the latest catalog is literally doubling our data. Published on May 26, 2026, this new catalog adds a staggering 172 brand new binary merger events to our records. To put that into perspective, just a year prior, GWTC4 had already doubled the previous counts. The speed of data acquisition here is accelerating at breakneck pace. We are transforming a once data-scarce field into one that is just brimming with measurable, trackable astrophysical corpses. This single update almost entirely doubles the total contribution from the LIGO-Virgo-Cagra network of ground-based detectors. We literally went from 218 known events to nearly 400 in the blink of an eye. And get this dataset is going to be superseded yet again by the end of the year when the third and final part of this observing run is released. It's moving that fast.
Now, don't get me wrong, individual showstoppers definitely still matter. Take the remarkably loud GW25114, for instance. It continues to provide an incredible scientific yield for testing the very limits of black hole physics. Even as we zoom way out to look at massive new population demographics, these extreme outliers give physicists the perfect laboratory to test the boundaries of general relativity and extreme gravity. That's the real beauty of a mature field. You have the statistical power to do both. You study the macro population and you interrogate the hyperspecific anomalies.
Which brings us to our third section, black hole flavors, and the two distinct subpopulations we are now seeing.
So what is this double dataset actually teaching us about the architecture of the cosmos? Well, population studies are now converging to show us two very distinct flavors, or subpopulations of black holes, and each points to completely independent formation channels. On one side, you've got a higher spin subpopulation covering a much broader mass range. The data suggests these might actually be formed by the hierarchical merging of an earlier generation, essentially older black holes eating other black holes to grow. On the flip side, we have a low-spin group, which we think are the first-generation remnants of collapsed stars.
This actually leads us to a massive theoretical puzzle. For a long time, theorists expected a steep decline in merger rates at around 40 solar masses. They thought this was caused by something called pair instability supernova. These are incredibly violent stellar explosions that completely obliterate the star. I mean, they leave absolutely no remnant behind. No neutron star, no black hole, nothing. This explosive phenomenon was heavily theorized to carve out a literal mass gap in that low-spin, first-generation black hole population.
But here is where it gets really interesting. Science thrives on friction, and the plot definitely thickens here. The sheer influx of new data from GWTC5 actually seems to weaken the evidence for this highly anticipated mass gap. While it reasserts the existence of the high-spin second population, that 40 solar mass gap is suddenly looking a whole lot less certain. And honestly, this proves exactly why these massive, maturing data sets are absolutely critical for finding the truth. A handful of detections, they can easily trick you with statistical flukes. It takes hundreds, if not thousands of events to really start separating actual cosmic architecture from random noise.
All of this recent progress, though, it's really just the prologue. Let's move to part 4, preparing for the flood.
Right now, we're actually sitting in a bit of a strategic pause. All 4 ground-based detectors have been undergoing massive upgrades since the end of 2025. They are gearing up for a timeline of rapidly escalating discovery potential over the next 5 years. They're going to come back online late this year for an intermediate 6-month run, which is brilliantly timed to coincide with the start of the Vera C. Rubin Observatory's LSSD operations. Then, in 2029, the 5th main observing run kicks off. And by 2031, LIGO India joins the global network. That is going to provide incredible distance from the existing detectors, which will massively improve our ability to pinpoint exactly where in the sky these signals are coming from.
And looking ahead to the next decade, things get wild. We are going to see an incredible technological leap. We're talking orbiting space-based interferometers like LISA, TianQin, and B-DECIGO, working alongside next-generation ground detectors like the Einstein Telescope and Cosmic Explorer. These space missions will link spacecraft over enormous distances using lasers, completely escaping the seismic noise of Earth. Because of their staggering sensitivities, these next-gen detectors will capture anywhere from thousands to literally millions of disparate events. In fact, there will be so many overlapping ripples in spacetime that scientists are going to have to model massive amounts of them simultaneously just to make sense of the data.
There's an editorial from Nature Astronomy that frames this beautifully. They wrote, "Surely this throwing open of the parameter space will sweep GW science off whatever feat it is currently finding. The sheer scale of the impending data flood is going to completely redefine a field that is, incredibly, only just now finding its footing. The field cut its teeth on decade-long hardware challenges just to get that single first detection back in 2015. But this maturation process, this necessary shift from bursts of extreme novelty to steady periods of heavy data crunching, it promises an unimaginably high scientific yield in the very near future."
So, I want to leave you with this to ponder. As this incredible science matures and we prepare for data sets containing millions of cosmic collisions, what previously invisible architectures of the cosmos are we about to uncover next? When the gravitational wave floodgates truly open, our view of the universe is going to look entirely different than it does today. Thank you so much for joining me on this explainer, and definitely keep your eyes and your ears on the stars.